Hello and welcome to the second video of the M2 chapter Variable Acceleration. P1 question here to get us going because of what we're going to do in this video. Find the coordinates of the turning points on the curve with the equation this, and for each turning point state whether it's a maximum or a minimum. Pause the video now, give this a go to refresh your memory if you've got time. Remember that to find a turning point we need to differentiate. That gives us 3x squared minus 12x plus 9, and then to find a turning point we have to set that derivative equal to 0, because where the gradient is 0 is a point on the curve that looks either like this or like this, gradient here 0, or potentially an inflection point like this where the gradient is 0 in the middle, just for a moment. So we set this equal to 0 and solve it. Here I can divide everything by 3 to make it easier. And we get x minus 1, x minus 3. So x equals 1, x equals 3. Now I have not finished yet. I need the coordinates, not just the x coordinate. So I should put these back into the y function here, find their y coordinate, and I still need to do this part. If x equals 1, then y equals 2. And if x equals 3, then I grab my calculator and calculate that y is equal to minus 2. Now there are a few different ways you can decide whether this is a maximum or minimum. Same with this. You can do a second derivative, or you can consider the coordinates either side of this point and this point, or you can consider the gradients either side of this point and this point. What I'm going to do is just do the second derivative, because this function is not so difficult. We get 6x minus 12, so when x is equal to 1, the second derivative is less than 0, therefore the point 1, 2 is a maximum. And when x equals 3, second derivative is greater than 0, therefore 3 minus 2 is a minimum. In this video, we're going to use ideas like this to solve kinematic problems. Kinematic is just a fancy way of saying problems of motion. So we already know that velocity is a change in displacement with respect to time, and that acceleration is a change in velocity with respect to time. Another way to phrase this is to use the phrase rate of change. Velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. And that phrase rate of change probably links with your pure work on differentiation. So writing these things as derivatives, velocity is the rate of change of displacement, we can write this. Velocity is the rate of change, or the differentiation with respect to t, of displacement. Sometimes you'll see an x for displacement, sometimes you'll see an s. Then we can do the same thing with acceleration. It is the rate of change of velocity, how the velocity changes with respect to time. And because we know v in terms of ds and dt, a can become a second derivative of displacement as well. We need to be able to use these ideas to differentiate a displacement function to get a velocity function, and to differentiate a velocity function to get an acceleration function, and then use it like we did in the previous video. Sometimes these questions will involve finding the turning points, which is why we did that starter question. So here we go, a few examples. Particle P is moving on the x-axis. At time t seconds, the displacement x meters from O is given by this function here. And you can see already we've used x instead of s in this case, which might seem a little bit weird if you tried to sketch this, because your x variable will be on what is usually the y-axis, and your t variable will be on what is usually the x-axis. Find the velocity of p when t equals 3. So on the surface of it, this is no different from what we did in the previous video. We just substitute in t and we find v, except the function we've been given is a function for x, not v. So we need to use our differentiation here already. V is the derivative of x with respect to t. So if I differentiate this equation, I get 4t cubed minus 32. and this is the function for velocity for this particle. Now when t equals 3, I can find the velocity. And that gives me 76. I can put units on this because x is given in meters and t is given in seconds, so this is meters per second. Part B, find the value of t for which p is instantaneously at rest. This is no different from what we did in the previous video, now that I've got the formula for v in terms of t. I just need to use it when v equals 0, instantaneously at rest. So when v equals 0, we have 0 equals 4t cubed minus 32. That gives t cubed equals 8, so t must be 2 seconds. Part C, find the acceleration of p when t is 1.5. So to find the acceleration, we need to differentiate the velocity function. So we need to differentiate this again. Acceleration is equal to 12t squared, and 32 differentiates to give 0. Now I have the acceleration formula, I just substitute in t equals 1.5. And that gives the answer of 27 meters per second per second. Next example. A particle of mass 6 kilograms is moving on the positive x-axis. At time t seconds, the displacement, take note, it says displacement, so this could become a negative, s meters, of the particle from the origin is given by this function here, where t is greater than or equal to 0. Find the velocity of the particle when t equals 1.5. Okay, again, take note of the words. We need to find the velocity. We've been given the displacement. So straight away, I'm going to need to differentiate this. That gives us 3t to the 1 over 2 minus 2/3 e to the minus 2t. Now I'm using that to find the velocity of the particle when t is equal to 1.5. Which my calculator says is 3.641, so 3.64 meters per second to 3 significant figures. Given that the particle is acted on by a single force of variable magnitude F newtons, which acts in the direction of the positive x-axis, find the value of F when t equals 2. This might seem a bit strange, a variable force, but this connects very closely through the very simple equation F equals ma. So for a mass of 6 kilograms, if you have variable acceleration, which of course is what our chapter is all about, then you must also have a variable force. So don't be put off by a question that talks about forces and variable forces. That's very, very closely linked with the acceleration of the particle. If you know the mass, or even if you don't know the mass, then you can call it m. So here what we really need to find first is the acceleration, and then we can use this to connect it with the force. To find the acceleration, we need to differentiate the velocity function. That gives us 3 over 2 t to the minus 1/2 plus 4 over 3 e to the minus 2t. When t equals 2, I can find the acceleration, and once I found the acceleration together with the mass, we can then find the force. So when t is equal to 2, putting that into this equation, 3 over 2, 2 to the minus 1/2, plus 4 over 3, e to the minus 2 times 2 is minus 4. And that gives me an answer of 1.0850 dot dot dot. Don't round that yet, because we still have another calculation to do. We've got F is equal to ma, the mass is 6, times the acceleration at time equals 2, 1.0850 dot dot dot, gives us a force of 6.510 dot dot dot, which I will now round to 3 significant figures. Don't forget, force is given in newtons. Actually, they've given newtons outside of the F here, and they want the value of F, so I guess technically I shouldn't include newtons there, otherwise it looks like 6.51 newtons. Our final example, a child is playing with a yo-yo. The yo-yo leaves the child's hand at t equals 0 and travels vertically in a straight line before returning to the child's hand. The distance, s meters, note that's distance, not displacement, of the yo-yo from the child's hand after t seconds is given by this function here for 0 to 3. Part A, justify the restriction 0 to 3 on the time. We've had a question like this before. The key point here is that they're talking about distance, not displacement, so immediately it makes me think beyond 3 seconds we probably get a negative value for this function. That's a very easy thing to check, and by putting that in the calculator I can see that when t is equal to 3, s is equal to 0, and this is another question that might benefit from drawing a graph, because we can see when t equals 0, s is equal to 0, so let me put that down as well. And we also know the general shape of this is a negative cubic. So if it goes through 0 and it goes through 3 and it has a general shape of this, then all I need to do is check that somewhere between 0 and 3 this is positive, in which case I can see that this loop here goes here and it has this shape. And I can see that very easily by putting in t equals 1, gives me 0.6 plus 0.4 minus 0.2 is 0.8. So this must go like this, and there'll be another value over there somewhere in the negative where s is 0 as well. So now I can say between 0 and 3 has positive distance values. Obviously we're not really interested in negative time, and anything above 3 we can see now that this is going to give us negative distance values, which we can't have because distance is a scalar. So let's say s is a distance, therefore must be positive, together with the fact that we started at t equals 0, then the time must be between 0 and 3. I won't write any more than that because I think the diagram gives the explanation better than anything I could write. Part B, find the maximum distance of the yo-yo from the child's hand, correct to 3 significant figures. Now in the previous video we had a situation where differentiating didn't really help us that much in finding the maximum speed of something, but in this case I can see from the diagram that the turning point between 0 and 3 is going to be the maximum point on this curve. So I can go ahead and differentiate, and so long as my time value is between 0 and 3, that will give me the maximum distance. So if I differentiate s, and that will give me 0.6 plus 0.8t minus 0.6t squared, and we know that that is equal to the velocity, and when the velocity is 0 gives us a maximum distance in this case. And to get something that I'm a little bit happier with, I'm going to multiply everything here by minus 5 to give me 3t squared minus 4t minus 3 equals 0. That I don't think is going to factorize, so I'm going to use the quadratic formula. 4 plus or minus the square root of 16 minus 4 times 3 times minus 3, 36, all over 6, which simplifies to give 2 plus or minus the root of 52 over 4 is 13 over 3. And of course time must be positive, therefore t must be the positive root of this, 2 plus root 13 over 3. But don't stop there, because we don't actually want the time as the final answer. What we want is the maximum distance, and this just tells us when that happens. So we need to put this back into the function for the distance to get the maximum distance. Putting that time back into that equation gives me 1.2129 ... rounded to 3 significant figures, 1.21. And the question gives us s in meters, so it's 1.21 meters to 3 significant figures. I hope that's enough for you to apply differentiation to some of the questions in exercise 2b, and maybe I'll see you in video 3 for integration.